Hey guys, so this video lecture we're going to be reviewing what we've talked about regarding factoring and the different kinds of expressions we've learned to factor. So the first thing is just finding greatest common factors, or the GCF. So let's look at a simple example. If I have the expression 12x plus 4, I'm looking at the two terms 12x and 4 and seeing what is the greatest factor that I can divide both terms by. And in this case it's going to be 4, and so I can take a 4 out, and if I divide both terms by 4 I'll get a 3x plus 1 left. And you can always check your work by distributing, so if I distribute the 4 back into the parentheses I should get what I started with, which we do. Let's look at another example. So let's look at 3x cubed plus 5x squared minus 4x. So notice now we don't have a number that we can take out as a greatest common factor. There's no greatest common factor between 3, 5, and 4, or negative 4. But we do have x factors in every single term. So we have an x to the third power, an x squared, and an x. So my greatest common factor in this case is just going to be x. And if I divide everything by x, I get 3x squared plus 5x minus 4 left over. And again, we can always check our work by distributing. When I do that, you should get 3x to the third power plus 5x squared minus 4x, which is what I started with. Okay, one more GCF example. Let's look at the equation 6x cubed y squared z to the 6 minus 30x squared y cubed z squared. So now I do have a common factor with my coefficients 6 and negative 30. I can take a 6 out of both of those. But I can also take variables out. I have an x cubed and an x squared in both terms, so I'm going to be limited by the x squared in the second term, but I can take an x squared out of both. Look at y's. I have a y squared in the first, a y cubed in the second term. Again, I'm limited by the smallest one, but I can take 2 y's out of each term. And then for the z's, the same thing. I have a z to the 6th power and a z squared. I'm limited by the squared, but I can take 2 z's out of both terms. So my greatest common factor is going to be 6x squared, y squared times z squared. And if I take this out, divide both terms by that greatest common factor, in the first term, the only thing I'm going to have left is 1x, and I'll have 4 z's left over. So remember, z to the 4th power times z squared is going to be z to the 6th power. I add those exponents when I do that distribution. So negative 30, if I take a 6 out, I get negative 5. And the only thing left of my variables is just going to be 1y. Both my z's came out, both my x's came out. Only 2 y's came out, so I have 1 left over. And so my final answer is going to be 6x squared, y squared, z squared times x z to the 4th minus 5y. And again, if you do the distribution, you should get back what you started with. I'll let you do this one on your own, but you should get the same expression that we started with. Okay, so the next thing I'm going to talk about is factoring quadratic equations. Remember, a quadratic equation, and review what that is. That's I guess really it's a quadratic expression. We don't have an equal sign here, but the definition is the same. So it's an expression where our highest exponent is 2, and we usually write them in the form ax squared plus bx plus c, or a, b, and c are just constant coefficients. They're just numbers. and your x is a variable. And again, it's the highest order x, or your highest exponent being 2, that makes this a quadratic. So let's look at a few quick examples. If I have the equation 3x squared minus 4x plus 7, this is a quadratic because my highest exponent is 2, and my coefficients, or a is 3, the b is negative 4, and c is positive 7. Let's look at another one. If I have x squared plus 19, so this one only has 2 terms. It's still a quadratic because the highest exponent is 2. And in this case, if there's no number written in front of our x squared, it's the same thing as being multiplied by 1. We don't have anything multiplied by x, so our b coefficient is 0. And then our c coefficient, whatever the constant is just going to be 19. Okay, so let's talk about how we factor these. Now, the first case I want to look at is the case when the first coefficient, whatever that a coefficient is, being multiplied by your x squared, is 1. Now, this is kind of a special case because there's a shortcut we can take advantage of. Let's look at an example. If I have x squared plus 7x plus 6, the first thing I need to do is I need to factor whatever my c coefficient is. So in this case, our c coefficient is 6. And the factors of 6 are 1 and 6, 2 and 3. And we're looking for a pair of factors that sum to whatever my b coefficient is. So our b coefficient is 7. I'm looking for factors that sum to 7. So it's going to be, in this case, 6 and 1. 6 plus 1 is equal to 7. And now, because our a coefficient is 1, we can just rewrite this as 2 binomials multiplied by each other, 2 binomial factors. And they're just going to be x plus 6 and x plus 1, because positive 6 and positive 1 are the factors we found. And that's the factored form of this equation. We just take those factors from our factor tree that add to our b term, and we can immediately go straight from there to our binomial factors. Now remember, you can only do this when the a coefficient is 1. If a is anything other than 1, you can't really take this shortcut. Let's look at another example. We have x squared minus 5x minus 14. It's quadratic. My a coefficient's 1, my b coefficient is negative 5, and my c coefficient is negative 14. So again, we're going to factor the c term. That was step 1. Factors of 1 and negative 14, negative 1, positive 14, 2 and negative 7, negative 2 and 7. And we're looking for the factor pair that sums to negative 5. So that's going to be 2 and negative 7. 2 plus negative 7 is negative 5. And so again, because a equals 1, I can immediately go to my factored form, which is just going to be x plus 2 times x minus 7. Now, I want to work this one out and show you why this works. And so this is really we're going to work through the whole procedure for factoring when a doesn't equal 1. But we're going to end up with the same thing. So really what we're doing here is we're splitting this b term, that negative 5x. I can just rewrite negative 5x as positive 2x minus 7x. I'm just splitting that middle term into 2 separate terms using the factors 2 and negative 7. And then I can group my first pair of terms and my second pair of terms in parentheses. So you have to be really careful here. Notice that I did not just put parentheses around the x squared plus 2x and around the negative 7x minus 14. If I do this, well, now this negative is distributed to both the 7x and the negative 14. So that's not the same thing. I cannot do this. So what I do is I write a plus sign and keep that negative with the 7x. And that keeps me from making this error. So next I'm going to take out an x from both terms in my first group. I have x squared and 2x. My greatest common factor is x. So if I look at my second group, I have a negative 7 and negative 14. And my greatest common factor between those two is negative 7. So I'll factor an x out of my first group, and I get an x plus 2. I take a negative 7 out of my second group, and I'm left with an x plus 2. Okay, so just as a brief aside here, this isn't part of the problem, but if I had the expression x times b minus 7 times b, where b is just some variable, my greatest common factor is going to be the variable b. So I can just take that out, and I get an x minus 7 left over. So we can do the exact same thing here. Instead of a b, our common factor in both terms is the entire binomial in the parentheses, the x plus 2. That's a common factor for both terms. So I can take an x plus 2 out, and I'm left with an x minus 7. And so again, this is the same thing we got using our shortcut method. The 2 and the negative 7 just go right into your binomial factors. Okay, now let's talk about factoring quadratics when our a coefficient, the thing multiplied by our x squared, is not 1. And I don't have a greatest common factor I can take out to make it 1. So let's look at the example 3x squared plus 16x plus 5. So there's no greatest common factor that I can take out. Nothing between 3, 16, and 5. So my a coefficient is 3, my b coefficient is 16, and my c coefficient is 5. Before we start, let's just write out all the steps we needed to do this. So we're going to multiply our a coefficient by our c coefficient. And we're going to factor whatever that is, and we're looking for factors that sum to whatever the b coefficient is. This is just like what we did before. Then we're going to split the b term using that factor pair that we found in step 2. We're going to group the first and second pair of terms in parentheses. And we're going to factor the greatest common factor out of each of those groups, out of each set of parentheses. And then we're going to factor the common binomial factor out of both terms. So those are what the steps are. I think they'll make more sense when we actually work through them with real numbers. Let's rewrite the problem. In step 1, we need to multiply a times c. So in this case, a is 3, c is 5, so a times c is 15. Second step, we need to factor 15, and we're looking for factors that sum to 16. That's going to be 1 and 15 in this case. And step 3, I'm going to split that b term into 2 terms. So the 16x becomes the 1x plus 15x. And again, that 1 and 15 come from step 2. That's the factor pair that sums to b. Step 4, I'm going to group my terms. I'm going to put a pair of parentheses around the first 2 terms, the 3x squared and the x, and then the second pair of terms, the 15x and the 5. In my fifth step, I'm going to look for greatest common factors in each group, in each set of parentheses. In the first one, in 3x squared and x, my greatest common factor is x. In the second set, at 15x plus 5, my greatest common factor is 5. And I'll take an x out of the first set. I have 3x plus 1 left over. Taking 5 out of the second set, and I have a 3x plus 1 left over. And so if I did it right, at this point, I should always have whatever's left in parentheses. It has to be the same in the first term there and the second term there. So I have x times 3x plus 1 plus 5 times 3x plus 1. That 3x plus 1 is repeated. If we get to this step and I don't have something in parentheses that's repeated twice, then I probably did something wrong. And then our final step is that we're just going to treat the entire thing, the x times 3x plus 1 plus 5 times 3x plus 1. We're going to look at that. And this is exactly the same as if I had x times b plus 5 times b. My greatest common factor is b. I can take a b out and I have an x plus 5 left over. It's the same concept, same thing, but now instead of a b, our common factor is 3x plus 1. So I can take a 3x plus 1 out, and I should have an x plus 5 left over. So that's my answer. And again, remember, you can always check your work by doing the distribution. So if I distribute the 3x plus 1 into the x plus 5, I should end up where I started, and I do. So that's my answer. Okay, and so the last thing we learned how to factor was the difference of squares. So let's review what that is for a minute. Let's work the problem backwards. If I have two binomials multiplied by each other, x plus 3 and x minus 3, I multiply these together, you get x squared minus 3x plus 3x minus 9. And so notice what happens to the negative 3x and plus 3x, those middle terms, when I do this distribution. They're going to cancel out, and I'm left with x squared minus 9. And let's look at another example. So we have, say that we have an equation 2x plus 5 times 2x minus 5. If I do this distribution, I get 4x squared minus 10x plus 10x minus 25. And again, notice what happens to those middle terms. Negative 10x plus 10x cancels out, and I just get 4x squared minus 25. And so there's a pattern here. Anytime I have two binomials multiplied by each other and they're the same except for opposite signs, so something that looks like a squared minus b squared, I can always factor this by writing it as the binomials a plus b times a minus b. And that's what the difference of squared is. So let's look at an example. If I have x squared minus 36. Well, my first term is obviously something squared. It's x squared, and 36 is 6 squared. So this is a difference of squares. It's something squared minus something else squared. And so to factor this, I just look at what's being squared, and I can put that into a couple of binomials. This is just going to be x plus 6 times x minus 6. Let's look at another example. If I have equation, the equation 16x squared minus 100. This one's maybe not quite as straightforward, but this is still a difference of squares. I can rewrite 100 as 10 squared. At 16x squared, I can also write as 4x in parentheses squared. So remember, when I have something in parentheses, that's squared. The squared is operating on both things. So 4 squared is 16, x squared is x squared. So 4x in parentheses squared is the same thing as 16x squared. And so to factor this, I can take what's being squared, my 4x and my 10, and put those into binomials. And my factored expression is just 4x plus 10 times 4x minus 10. Okay, let's do one more. Let's look at 2t squared minus 50. So this one, it kind of looks like a difference of squares. There's a t squared, but 50 is not a perfect square. But what I can do is, when I look at this, I notice that the two terms 2t squared and negative 50 have a greatest common factor. I can divide both of those by 2. And so if I take a 2 out, I'm left with just a t squared minus 25. And now that is a difference of squares. T squared minus 25, and 25 is 5 squared. So I can factor this as t plus 5 times t minus 5. And remember, we still have the 2, the greatest common factor that we started with. So 2 times t plus 5 times t minus 5 is my final answer there.